What's going on, guys? Welcome back. In this module, we are going to be covering protocols with Swift. So let's go ahead and just jump into the documentation we have here before we get started with the code. So a protocol defines a blueprint of methods, properties, and other requirements that suit a particular task or piece of functionality. That protocol can then be adopted by a class, structure, or enumeration, and we saw an example of that in our last video, and we'll cover that in a second, to provide an actual implementation of those requirements. Any type that satisfies the requirements of a protocol is said to conform to that protocol. So really quickly, guys, if we go back to our Enums guy, we used a protocol in this color enum. This case iterable guy right here is a protocol that allows us to treat our enum as, or all of the cases as an array, which was really cool, right? So let's go ahead and jump into some real life examples of protocols that we might see before we jump into the code. So you might have security protocols at airports, banks, or government facilities, right? There are certain rules that have to be adhered to or followed in something like an airport to meet the requirements of a security protocol. You might also have safety protocols in hospitals, right? You have to follow certain rules to adhere to the safety or sanitary protocols of a hospital to make sure that you are operating as a legitimate facility, right? Evacuation protocols as well. For example, if there's an earthquake in your city has evacuation protocols in place that are those are a set of rules that have to be followed in a particular order, or rules that have to be met in order to meet this evacuation protocol, right? But when that goes into effect, those rules have to be followed. And then in something like a factory, or like if you're a mechanic, there's instructions to follow to complete a task, right? So for example, if you're a mechanic for like an F1 team and you're doing some sort of engine maintenance job, there's probably a protocol to follow, like a set of steps that you follow to make sure that that process is as standardized as possible, right? So those are some real life examples of protocol, guys. And the common theme between all of these things is that there's just a set of rules that you have to follow or adhere to, or like requirements that you have to follow when you conform to a particular protocol. So we have the same sort of structure with programming in Swift, and we're going to jump into that now. Our first section is just going to cover the syntax, guys, so how to create and type out a protocol. So let's go ahead and make a mark for our syntax here. We're going to say protocol, and you notice that that is a key word here that is recognized by our compiler, and we can just say some protocol. And then you just open up some brackets, and then you can just say like stuff goes here. So this is the basic syntax of a protocol, guys. You define it. You use this keyword, and then everything that goes inside of here is what is known to be the requirements of the protocol. So let's go ahead and make an actual example. So let's make an example, and let's go ahead and create a protocol, and we're going to call it identifiable. And we are just going to implement one property here, and this is how you do that. We're going to say you need to have an ID. And you are going to type out this bracket with get in the middle. So let's go ahead and do a quick breakdown of what exactly this means. So we've created this identifiable protocol. So basically, we're going to have some sort of struct or enumeration that is going to conform to this protocol. And the requirements are that it implements this ID property. So anything that conforms to this protocol is going to be identifiable. And in order to meet the requirements of that protocol, it's going to have to implement this ID. So in the protocol, you just define sort of the interface of what the conforming or adopting structure is going to have to implement. And then the thing that conforms to the protocol will then in turn implement that thing. So let's go ahead and see what I mean by that. So let's go ahead and make maybe a struct for a user again. And let's go ahead and just say we're going to have a name and an email maybe, right? Or an age. Let's do age. That's easier, right? So pretty straightforward. We've seen this before. And let's go ahead and now conform to this protocol, guys. Let's imagine we want our users to be uniquely identifiable, right? So that we can distinguish one user between the next with some sort of unique ID. This is an extremely common thing in apps that have users. So what we would do is add a colon here and conform to this protocol. You see here we are conforming to the identifiable protocol. Here's our protocol right here. And you guys will notice if I try to run my code, I'm going to get an error. And this is because our compiler is recognizing that we're conforming to this protocol, but we're not implementing this property. So this is the foundation of a protocol here, guys. When you conform to the protocol, you have to follow all of the things that are listed in that protocol. In this case, there is a variable that is an ID. It has to be a string, and we have to give it a value. That's what this get guy means, right? So lucky for us, the Swift compiler is pretty awesome, and we can just go ahead and implement that property there. And now I could just give this a value. I could either do that when I create the user, or I could give it a default value here. But let's go ahead and just create a couple users, guys. We can say let user1 equal user ID, and I can just go ahead and say nsuuid.uuid string, name, John Doe, age 30, right? And then I could say let user2 equal user, and it's going to make sure I implement that ID there as well. Name, Kelly Johnson or something, I don't know, and she's 24, right? But guys, the whole point of this, I need to import foundation up at the top, is just to make your code a little bit more robust, you could say, right? So I know that now, anytime I create this user, it has to have an ID. And we'll dive deeper into how this helps us out a little bit later on. This is just to give you guys an idea of how exactly a protocol works and what an implementation of that looks like, right? So I could create like another struct, like let's imagine I have a product or something, and also make sure that conforms to the identifiable protocol. And it will just make sure that when I create this structure, it requires me to implement that ID property, right? Because each product will probably need some ID. It would probably have a price, and it would probably have a name, right? So this just enforces you to make sure you have that ID property. You could easily just remove that protocol and just keep the ID property there, but we'll see how this helps us out a little bit later. This is an extremely common thing in SwiftUI as well, guys, which we will get practice with in the SwiftUI bootcamp. All right, let's keep going. Right? Just a quick break from the tutorial, guys. If you want access to the full intermediate and advanced fundamentals with Swift course, head over to the website at stephancodes.com. The link is in the description. And in the courses section, you guys can scroll down to find the fundamentals courses, and you will see the full pro version of this course here, guys. So we cover a bunch of additional topics, and that include generics, classes, the difference between classes and structs, memory management with retain cycles and all of that stuff, extensions, and pretty much everything that covers all of the intermediate and advanced stuff with Swift. So make sure you guys check that out to get your programming skills as an iOS developer to the next level. So let's go ahead and get back to the tutorial, guys. Thanks for watching, right? So let's go ahead and get a little bit more advanced. So let's go ahead and create another example. We'll say shapes example. And this is really going to showcase the power of protocols here, guys, because we can sort of treat them as abstract types, right? And we're going to see how that works here in just a second. So let's go ahead and create another protocol, and we're going to call this shape. And we're just going to say that a shape protocol requires me to give the number of sides. That's an integer, and it's going to require me to get that. It's going to require me to name my shape, which is a string, and it's going to say you have to give me that. And then it's also going to have a function to get the area for me, which is an integer, okay? So, oops, I typed that wrong. So this is my shape protocol. And guys, we see here that we can have properties of different data types, and we can also have functions, right? So now any class or structure that conforms to the shape protocol has to implement all of these things. So let's go ahead and see if we can accomplish that. Let's create two shapes. We'll create a rectangle, which will conform to the shape protocol, and we'll create a square, which will also, oops, man, can't type today, which also conforms to that shape protocol. Cool. So guys, you can just go ahead and hit fix here and hit fix here. And you'll notice that now both of my structures are going to require me to add all of these properties and functions, right? So now we have two different classes, or structures rather, that are conforming to this shape protocol. And this makes sense, right? Both rectangles and squares are shapes. But we might want to implement something differently with a rectangle than we do with a square. For example, how we get the area of this, right? So this is where this starts to get interesting. So our rectangle is going to require us to supply it with the number of sides, the name of the shape, and then it's going to require us to implement this function that is going to say, hey, how do you get the area for this particular shape? So here, guys, we can add our own custom properties to this as well. So we are going to need a width and a height for our rectangle, right? And guys, you can change these to let declarations as well, but in the protocol, they have to be treated as variables. If you were to try to change this to let, you can't sort of have this getter for a let property, right? So let me just go ahead and return like 0 for now and return 0 for now, so we can make sure our compiler builds. And you guys notice that here, let declarations cannot be computed properties, so we have to make this a var. So, but when in the implementation of the protocol, it doesn't have to be treated as a variable. You can follow all of the struct semantics as you see fit with let and variable declarations. None of this stuff is going to change for our shape, so we don't have to make any of them variables. So this is what we're going to stick with for now. So how do we calculate the area of a rectangle, guys? We just say return width times height, right? But getting the area for a square is slightly different, right? A square doesn't necessarily need a width and a height because we know the width and the height will be equal to each other, right? So here we just need a property for our side length. So let's go ahead and say let side length be of type integer, and we can change these to let properties as well. And our square will have a different implementation of that get area function, right? We're just going to say return side length times side length. So we can see here that we have this get area function declared in our protocol, guys, but we get to implement it in each individual struct that conforms to that protocol. So this is our sort of interface definition of the function, and this is the implementation of that function. And we can see here that it gets implemented differently in both shapes. It's the same function, just implemented differently, right? So this is what's known as being polymorphic in object-oriented programming, right? We have some interface and we get to conform or adopt that interface, or this protocol, as you could call it in Swift, and we get to implement that function differently in each object that conforms to the protocol. And you guys can imagine if I created more shapes, it would just really help me build a concrete data model for all of my shapes here, right? A sort of concrete mapping of each shape. Each shape has to conform to all of these things, and then we could choose the different implementations of each shape, but they all share this stuff in common. So that really helps us build a robust data model in our programs, guys. And that's another one of the benefits here. Like if I was coming into this code and I saw how a rectangle and a shape was, and a square was created, and I see that it's conforming to this protocol, and my company goes, hey, we need you to create another shape. Let's create a triangle or a circle or a trapezoid or a polygon or whatever it may be, right? I would say, okay, let me look at how these two were created. I can see that they conform to the shape protocol, so I know that for the next shape I create, I'm going to have to do that as well. But there are added benefits apart from just like the nice to haves there, right? Like technically, these things don't have to conform to this protocol, right? And everything would still work as expected up to this point. But let's go ahead and see what conforming to this shape protocol actually allows us to do, guys. So let's go ahead and create two instances of these shapes. Let's create a rectangle, which is a rectangle. Number of sides is going to be 4. Name is rectangle. Width, and we can maybe say it's 5 by 10, right? And then let's create a square. Number of sides is 4. Name is square. Side length is maybe, let's say, 8, right? So something that's actually really cool that protocols allow us to do is treat this rectangle and square as this abstract shape type. So guys, what I can do is, let's imagine I wanted to add all of my shapes to an array. So I could say var shapes, and I can actually treat this protocol as an abstract type. And then I can append, I could say shapes.append rectangle and shapes.append square. So even though these are two completely different structs, because they both share this conformance to this protocol, I can create an array of that protocol type and add any object to that array that conforms to that type. So once again, guys, what this allows me to do is take these two completely different structures and add them to a single array. And that is extremely powerful here. So let's go ahead and see how we can actually utilize this. So I could go ahead and just loop through this array now, and I could say print shape is, and I could say shape, and let's go ahead and just say dot. And you guys will notice that I only get access to the protocol properties and functions, right? Even though I'm looking at, in the first item of my array, a rectangle, I don't get access to the width and the height of the rectangle because this is being treated as a shape, which is of this protocol type, right? So I can say shape.name, and shape area is shape.getArea. So let's go ahead and take a look at what happens when I run that. And you guys will notice that my shape is a rectangle and the area is 50, and then my shape is a square and the shape area is 64. So this is extremely powerful, guys. And I'll give you an example of how this might be used in a real life mobile application. But first, I want us to go over what might happen if I suddenly remove this conformance to that protocol on my square type. It says argument type square does not conform to expected type shape. And Swift is smart enough to fix this for me. Or actually, no, this wouldn't fix it. We can't just cast this as a shape because it needs to actually conform to that shape protocol. But the only reason we're allowed to do this, guys, is because both of these things conform to that shape protocol. So let me just go ahead and remove this casting. We will go over how to actually look at a protocol type and cast it to its original concrete type, guys. And you're going to hear me use that terminology a lot. Protocols are referred to as abstract types because things have to conform to this protocol. Like, we can't just initialize a shape the way we can initialize a struct. So a struct is referred to as a concrete type and a protocol is referred to as an abstract type. So let me go ahead and add that in our notes. Protocols are abstract types, structs, classes, and enums are concrete types. So concrete types conform to or implement abstract types, and then we can treat those concrete types as these abstract types, right? So I know that's a lot of weird programming jargon, but this is a very clear example of how that works, right? And I told you guys I would give you a real life example of how this works. Let's think of an app like Instagram, right? So when you're putting that Instagram feed together, guys, that is like an array of posts. So let me go ahead and model this out for you. So you might have a struct for a post. You might have a different type of struct for a reel, right? So how do you combine posts and reels into a single feed, right? You need a single array that you loop through to create that feed in the application. Well, this is exactly how you would accomplish that, by using a protocol, which is an abstract type. So we can go ahead and model that out. We could say, hey, let's make a protocol, and we could call it like feed item protocol or something, right? And this would have all of the stuff that both of these things need to conform to, like a caption, which is a string that you have to get, right? And then it also might have some sort of media type. And this would be some sort of custom media type, right? Whether it's the post or like the image URL or the video URL or whatever. But both of these things would then conform to this feed item protocol. And then you would be able to add all of those things to a single array and render all of those items in your feed, right? And when you have a reel, you might have your own logic attached to that, which you could just add to this struct. And then when you have a post, you might have your own logic or properties attached to that, which you would add to this. And I will show you guys how to actually cast these things as like their concrete types right now. And we're actually going to come back up to our shapes guy for this because we have a little bit more of an implementation with these shapes than we do with this. This was really just an example to show you guys how you might use this in a real life situation. So casting, guys, this is important as well because sometimes you need information about the concrete object itself, right? You might be too limited with the protocol data that you have, right? Like let's say I want to get the width and the height of the rectangle. I can't get that through the protocol, right? I just get number of sides, name, and the area function. So this is something we're going to cover in more detail when we get into our classes module. But guys, I could go ahead and just add an if statement, an if let statement. I could say if let shape equals shape as a rectangle. Then I can treat this shape as a rectangle now. So this is like a conditional casting. It's going to say, hey, if this shape's concrete type is a rectangle, then I could say print shape side length is, or sorry, shape width. And we can now say shape dot width. And that is a property that is unique to my rectangle, right? And then I could also say print shape height is shape.height, right? But guys, I also have access to the protocol functions. So now it's sort of treated as both things. I can treat it as my abstract type, which is my shape protocol, but now I've also successfully casted it as a rectangle, and I could do the same thing for a square, right? So let's go ahead and rerun this code and see what that gives us back. Let's see if that casting was successful. So you guys notice that I get shape, width, and height is 5 and 10, which is exactly the values of my rectangle, but nothing prints out for that square, right? So we could go ahead and add an else block here and say print shape is not a rectangle. And we can run this again just so you guys can see exactly how this is working. And let's see, it's running. I think I need to run that one more time. Yeah, sometimes the playgrounds get a little weird. Okay, check it out. All right, so shape width 5, 10, shape is rectangle, shape is square. And then this is all the rectangle stuff, right? The rectangle stuff stops there. And then I go and get, let's see. Okay, I think this is hanging around from previous runs. But the most important thing here is, guys, we get shape is not a rectangle. So it hit this else block when it got to the square because this casting failed, right? So that is how you can treat your protocol abstract type and sort of convert it back to, or also treat it simultaneously or polymorphically, as it's referred to formally in object-oriented programming terms, as your concrete type. So that's super, super interesting there, guys. So next up, I want to move on to a couple more examples of protocols, and then we are going to wrap this video up. So guys, we can also use this with enums as we saw before. So let's go ahead and make a protocol called like describable, which is just a protocol, and it's going to have a single property called description, which is going to allow me to get that description. And then let's make like an enumeration for something like an account type, right? And we can treat this as like a different account types a user could potentially have. So let's imagine we have like basic, pro, and pro plus, right? Okay, so these are the different account types my user could have. Let's go ahead and add this to my user struct, right? So let's go ahead and make an account type property. Right, so this gives you guys an idea of how to create different user types. So now we have to add that to each one, account type, and we could make this guy .basic, and we could make, let's see, Kelly Johnson a boss, and she's got a Pro Plus account. She's balling, right? Okay, so now we can distinguish our account types between our users using this enum. Okay, so where does the describable guy come in? Well, let's go ahead and implement this. Let's say we want this to enum to be describable, right? And now we have to implement this description property. And let's imagine that we want to sort of have a different description for each one of our enum cases, right? So we're going to go ahead and implement this description property, and it's going to be a computed property. And we saw this in our enums tutorial, guys, where enums can have description or computed properties that are unique to each individual case. So we can sort of see how all of this is coming full circle, and how we use previous concepts from previous tutorials in combination with other tutorials, right? And it's very important to touch on that, guys. Programming, just like math, builds on itself. So you need to make sure that you have a strong foundation in each one of these modules before you move to the next, so that you don't get lost along the way. Imagine that you're building sort of a structure, and that is your knowledge. If you don't have a solid foundation on one level, the next level of your understanding will be very shaky and flimsy. And ultimately, if you keep doing that, the structure will collapse and you will never get a job as a programmer, and you'll be broke forever. So don't do that, bro. Okay, anyway, let's go ahead and implement this now. Let's do a switch through our self, and we can say return basic account, return pro account, and here we could return pro plus account. And let's go back up to our guy right here, and I could say print user1 dot account type dot description, print user2 dot account type dot description, and just go ahead and run this bad boy right here. And we will notice that, hey guys, check it out. Oh, what's going on? Okay, it's saying it can't find the account type in scope, and that's just because I think we need to go ahead and add this stuff like above our user guy. So just go ahead and cut that, guys, and maybe go here and add it. And I think we would be good to go there, right? So let's go ahead and print that stuff. And yeah, so we have a basic account and a Pro Plus account. So that just gives you guys an idea of how Enums can adopt protocols as well. So that is really going to wrap it up for our protocols tutorial, guys. That gives you everything you need to know with protocols for now. There's obviously a lot more that we can do with them, but that is going to get covered in more of the advanced stuff and other courses like the networking tutorials and the pro courses. This is really just to give you a foundation with protocols, how they're used and how they work. So in the next one, guys, we are going to be covering classes, which is a super important concept in object-oriented programming. And we're going to go over how classes, structs, enums, and protocols all sort of relate to one another to really get a solid understanding in object-oriented programming, which is necessary if you want to become a programmer on any sort of level and build any type of software, right? Object-oriented programming is necessary to know, and you will not be able to build apps or any type of software or program without this knowledge. So hope you guys are excited for that. Let's keep going with this stuff. We'll see you there. Peace.